Hello. I'd now like to have a look at a particular application of using R to numerically solve differential equations. The example that we'll look at is using R to solve the so-called Lotka-Volterra predation equations. They're a pair of coupled differential equations in that we have two of them and they are linked. Here is the instantaneous rate of change of the density of the prey population, and here is the instantaneous rate of change of the predator population in terms of its density. What we have here is the prey population effectively changing, growing or declining exponentially according to the size of R when there is no predation. However, we also have a loss of prey caused by predation, and what we use here is a constant A and then a mass action term where the more predators there are, the greater the loss of density of the prey population. But also, the more prey there are, the more predators will encounter them, and so the greater the instantaneous rate of loss. Likewise, predators, in the absence of prey, would tend to decline in numbers, and yet when there are prey available to consume, then predators are giving birth to new predators, and we have a constant here, F, to represent that. Here again we're assuming mass action, in that the more predators there are and the more prey there are, the greater the contribution to the predator population in terms of its increase in density. Now, the equations are called the Lotka-Volterra equations because in the mid-1920s, uh, Vito Volterra, a professor of differential equations in Italy, developed a simple series of predator-prey models and published them in Nature. However, Alfred J. Lotka, a demographer and chemist, had actually 2 years before published a very important book called The Elements of Physical Biology, and in that book he had detailed precisely the same type of predator-prey model. Because they were effectively independent discoveries, they've become known as the Lotka-Volterra equations. Well, how do we go about solving them? Well, you'll remember that one way to solve them in R is to use the ordinary differential equation uh, numerical routine called ODE, and that's in the dsolve package. You'll also remember that the ODE is particularly fussy in that it requires the state variables. It also requires the times over which you want to do your integration. It requires the function, and it also requires a list of parameters. So let's get started. Let's, of course, first load our libraries of dsolve, and because we'll be using a graphics package, we'll also be using the library lattice. Here are our constants, and I've just made up some values here for R, A, F, and B. They're the constants in the Lotka-Volterra equation. Now, what I'm going to be doing is to pass them into a vector P with all our parameters, but I'm going to pass them by name. So it may seem a little bit strange, but I'm saying R is equal to R, and that's because here the name of that element is now given R, and we're saying that it's equal to this value here that we've ascribed. And likewise for the start conditions for our dynamical variables, which are n and p, we're going to be giving them by name. So it's n is equal to 25 and capital P is equal to 5. Now you'll remember that the ordinary differential equation function requires a function to integrate, and it also requires a set of times. Here what we're going to be doing is integrating between the times 0 and 200, Now it's integrating continuously, but we would like it to report out just every 0.1 unit of time. Now here is the main part of our ODE solver. We're going to be saying the output from the Lotka-Volterra model is this. Of course, we need to define our function, but everything else is all set out here. Now let's have a look at our function. We've called it predator-prey Lotka-Volterra, and we're defining it as a function here. You've got to be very careful with the brackets here. We're saying n is the very first element of y, which we've just set. We're saying p is the second element of y, which we've defined. Now, using this with and adds.list statement, we can use the individual names that we had for r and n within this individual function, rather than have to go to p square bracket 1, p square bracket 2, etc. So it's really quite useful. Now, the way we have defined our function for it to be of use to the ODE, we have to return a list with the first dynamical variable and the second, and that's just what we're doing here. You'll notice these are the rate equations. There is nothing special about dn dt, it's just the first rate equation, and that's the second rate equation. Now, if we solve that between 0 and 200 for those particular parameter combinations, all it requires us to do now is to plot it out, and I've used matplot. The very first part is time, and then for LV out, the second and third column will be for n and p, and by calling up matplot from the lattice, this is what we get. The very familiar predator-prey cycles. Or if we wanted to plot directly prey density against predator density, i.e. we look at the dynamics in phase space, so time is implicit rather than explicit, we can simply plot prey against predators, and this is the type of diagram that we would get. It should be familiar because you've just seen it in those papers from Nature by Vito Volterra, and also from the Elements of Physical Biology from Lotka. How can we make that model more realistic? Well, there are many things we could do to make it more realistic, and perhaps one way is to consider that prey would not continue to increase indefinitely in the absence of a predator, but may rise to something of a carrying capacity, rather like we had in the simple logistic equation here. So that's the only change I've made there. What it would entail is a simple change to our individual function here. Now, of course, I could define a parameter and call it k in here, but for simplicity, I'm just simply putting n upon 1,000, so I don't need to define it. That's our value of k that we've got. Now, this is what we would get when we actually plot it out. Here, instead of the familiar cycles, what we're actually getting is movement towards an equilibrium. It's damped oscillations towards an equilibrium of our predator and prey. And likewise, this is what we would get when we plot it out in the phase space. So gradually, very gradually, it's all boiling down to a single equilibrium of predator and prey density. Thank you for listening to this R-Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.